Before we can ask whether we are near the end of cosmic time, we must answer something more basic. What is cosmic time at all? In daily life, time feels linear, uniform, human-scaled. Seconds, minutes, years, these units are tied to Earth's rotation, Earth's orbit, biological aging. But cosmic time is not measured by clocks on Earth. Cosmic time is the age of the universe itself, measured from a specific physical event, the Big Bang, approximately 13.8 billion years ago. This is not a philosophical guess. It is supported by cosmic microwave background radiation, expansion of space, the Hubble-Lemaitre law, and relative abundances of light elements, hydrogen, helium, lithium. In cosmology, cosmic time is defined as the time measured by a hypothetical observer who is moving with the expansion of the universe and sees it as isotropic, the same in all directions. This definition comes directly from Friedmann-Lemaitre-Robertson-Walker cosmology, the mathematical framework underlying modern cosmology. In this framework, every galaxy moving with cosmic expansion shares the same cosmic time. The universe has a shared age. So when we say the universe is 13.8 billion years old, we mean it's tempting to think the universe has always existed or will exist forever in the same way, but physics tells us something subtler. The past is finite. Evidence shows space itself emerged from a hot, dense initial state. Time, as we understand it, began with the Big Bang. This is not just philosophy. It follows from Einstein's general relativity, observed expansion of space, and the singularity marks the limit of current physical theories. The future may be vastly longer, but not symmetric. The future of the universe is not simply a mirror of its past. It will unfold under very different physical conditions. This asymmetry is crucial. Physicists do not treat cosmic time as one uniform block. Instead, they divide it into eras based on dominant physical processes. For example, radiation-dominated era, matter-dominated era, dark energy-dominated era. Later, theorists extend this idea far into the future. Stelliferous era, stars shine. Degenerate era, stellar remnants dominate. Black hole era, dark era. These classifications are based on thermodynamics, nuclear physics, and gravitational dynamics, not speculation. This allows us to ask a meaningful question. Which era are we in? Early? Middle? Late? Asking whether we are near the end of cosmic time is not about drama. It connects directly to entropy and the arrow of time, energy availability, formation of complex structures, conditions for life and intelligence. If life depends on stars, free energy, chemical complexity, then the timing of our existence is not random. The universe may last trillions upon trillions of years, yet the era that allows stars, planets, chemistry, and observers may be very short. So the real question becomes, are we early in the universe's total lifetime or late in the universe's meaningful lifetime? This distinction will guide everything that follows. To ask whether we are near the end of cosmic time, we must confront an uncomfortable truth. The universe does not end in a single way. Its fate depends on expansion rate, dark energy, thermodynamics, quantum effects. Let's examine what physics actually predicts. Observations show distant galaxies are moving away from us. The farther they are, the faster they recede. This is described mathematically by v equals h0d, where v is recession velocity, d is distance, and h0 is Hubble constant. But the key discovery came in 1998. The expansion of the universe is accelerating. This was confirmed by Type 1a supernova observations and Nobel Prize in Physics in 2011. The acceleration implies the existence of dark energy. In Einstein's equations, this appears as lambda, the cosmological constant. Dark energy does not dilute as the universe expands, dominates the future dynamics of the cosmos. If current measurements are correct, expansion continues forever. Galaxies become increasingly isolated. Under the standard LCDM model, no big crunch, no sudden collapse, no fiery apocalypse. Instead, stars burn out, matter spreads thin, energy gradients disappear. This leads to the heat death of the universe. Heat death is not destruction, it is maximum entropy. According to the second law of thermodynamics, delta S greater than or equal to 0. Entropy increases. As time progresses, energy becomes less useful, work becomes impossible, complex structures cannot form. The universe approaches thermal equilibrium. Current age of universe 1.38 times 10 to the 10th years. End of star formation 10 to the 14th years. Proton decay, if it occurs, about 10 to the 34th years. Black hole evaporation, the largest, 10 to the 100th years. These numbers are not guesses. They come from nuclear physics, Hawking radiation equations, and general relativity. Compared to these scales, human history is effectively zero. Even stellar history is brief. If the universe lasts trillions of years, then why do we exist so early? Why during the brief era of stars? Why not in the unimaginably long future? Most people assume the universe is just beginning. Physics suggests the opposite. Astrophysicists Fred Adams and Gregory Lowling described the cosmic future in detail. They identified the current era as the stelliferous era, the age of stars. This era began about 100 million years after the Big Bang and will end about 100 trillion years from now. But here's the crucial part. Star formation peaked billions of years ago. Observations show star formation peaked about 10 billion years ago, and it has been declining ever since. We're living after the peak, on the downward slope. Most stars that will ever exist have already formed. This is a measurable astrophysical fact derived from galaxy surveys. Life requires carbon, oxygen, nitrogen, and iron. These elements are forged inside stars and in supernova explosions. Early universe, too simple, mostly hydrogen and helium. Far future, too cold, too diffuse. The window for complex chemistry is narrow. If intelligent observers require long-lived stars, heavy elements, and stable planetary systems, then observers can only exist during a brief fraction of cosmic time. This suggests we may already be living late in the era that allows observers at all. So now the question becomes precise. Are we near the end of the universes? No. Are we near the end of the universe's life-supporting era? Possibly yes. This is where physics begins to touch philosophy. In modern physics, the most precise operational definition of the direction of time comes from thermodynamics, not relativity. The second law of thermodynamics states ds dt greater than or equal to 0, where S is entropy and T is time. This law is statistical, not absolute, but for systems with extremely large numbers of degrees of freedom, such as the universe, violations are negligibly improbable. Time has a preferred direction because entropy increases. Observations of the early universe via the cosmic microwave background show extreme uniformity, small temperature fluctuations, about 10 to the negative fifth. Paradoxically, this corresponds to a very low entropy state. This was first emphasized quantitatively by Roger Penrose, who estimated that the phase space volume corresponding to the universe's initial state is extraordinarily small, about 1 part in 10 to the 10 to the 123rd. This low entropy beginning is not explained by known physics and remains an open problem. Unlike gas in a box, gravitational systems behave differently. For gravity, uniform matter distribution equals low entropy. Clumped matter, stars, galaxies, black holes equals high entropy. As the universe evolves, matter collapses under gravity. Entropy increases via structure formation. This process defines much of cosmic time evolution. Current entropy is dominated by supermassive black holes. Black hole entropy is given by the Bekenstein-Hawking formula. S equals kc cube over 4g h bar times A, where A is the event horizon area. Supermassive black holes already contain most of the universe's entropy today. As time progresses, black holes merge, total entropy increases further. Eventually, Hawking radiation dominates entropy production. Entropy increase implies decreasing availability of free energy, reduction in temperature gradients, decline in processes capable of doing work. This is why star formation slows, complex structures become rare, long-term evolution becomes increasingly simple. This is not speculative, it follows directly from thermodynamic constraints. All physical processes require free energy. F equals U minus T times S. As entropy S increases, free energy F decreases. Fewer processes remain dynamically accessible. Life, stars, and observers all require sustained free energy flow. Large-scale galaxy surveys, SDSS, Hubble, and JWST, show star formation peaked at redshift equals 2, roughly 10 billion years ago. Since then, gas reservoirs depleted, galaxies become red and dead. Star formation rate declines exponentially, mathematically modeled by SRF of T proportional to e to the negative t over tau, where tau is on the order of several billion years. Stars convert mass to energy via nuclear fusion, E equals mc squared, but only about 0.7% of hydrogen mass converts to energy. Stellar fuel is finite. No known mechanism replenishes it on cosmic scales. Even red dwarfs, the longest-lived stars, will exhaust fuel within 10 to the 13 years. Photon wavelengths stretch, redshift, temperature scales as T proportional to 1 over A of T, where A of T is the scale factor. This guarantees cooling, reduced reaction rates, suppression of structure formation. An observer is not abstract. It is a thermodynamic system that requires energy flow, low entropy gradients, stable matter structures. Thus, observers can only exist during periods when free energy is abundant, entropy gradients persist. Define T observed as time window allowing observers, T total as total lifetime of the universe. Current models indicate T observed over T total is much less than 1. Even though T total tends to infinity, T observed is finite. This is a quantitative result, not philosophy. Future epochs include the degenerate era, white dwarfs, neutron stars, black hole era, dark era after black hole evaporation. None of them provide sustained energy gradients, chemical complexity, or stable environments for observers. From physics alone, the universe is not near its temporal end. It is likely past the peak of structure formation. It is within a narrow window where observers are physically possible. In cosmology, early and late are not subjective concepts. They are defined using measurable functions of time, such as star formation rate density, matter density, radiation density, dark energy density, and entropy production rate. To determine whether we are late, physicists ask, relative to which physically relevant process? This distinction is critical. The cosmic star formation rate density is one of the best measured functions in observational cosmology. Data sources: Hubble Deep Field, Sloan Digital Sky Survey, SDSS, GOODS Survey, and JWST early release observations. Empirical result: rho.star of Z peaks at Z approximately 2. This corresponds to approximately 3 to 4 billion years after the Big Bang, approximately 10 billion years before the present. The universe has already passed its peak star production phase by a large margin. Integrating the star formation rate over time gives a striking result. More than 90% of all stars that will ever form already exist. Remaining star formation is slow and declining. This is not model-dependent. It follows directly from observations of gas depletion in galaxies. Even though the universe may last trillions of years, most stellar light exists in the first 10 to 20 billion years. The total energy output from nuclear fusion in stars is finite. energy generation rate, E dot of t proportional to rho dot star of t. Thus, energy production peaked in the past. The universe today is already in an energy decline phase. This means, from an energetic perspective, we are already living in a cooling universe. Let T0 equals 1.38 times 10 to the 10 years, current age, and T end greater than or equal to 10 to the 100 years, heat death scale. Then, T0 divided by T end approximately equals 10 to the minus 90. By duration alone, we are extremely early, but by structure, energy, and complexity, we are late. This mismatch is one of the most important quantitative facts in modern cosmology. Dark energy does not merely expand space, it removes causal contact between regions of the universe. Key equation, Friedmann equation with lambda, bracket A dot over A squared equals 8 pi g over 3 times rho plus lambda over 3. As time goes to infinity, lambda dominates. Expansion becomes exponential, A of t proportional to e to the ht. In an accelerating universe, there exists a cosmic horizon. Light emitted beyond this horizon will never reach us. This is not hypothetical. It is a direct solution of general relativity. Interesting fact, in the far future, observers in our galaxy will see only the local group, no evidence of other galaxies, no observable expansion. Reference, Krauss and Scherer, General Relativity and Gravitation, 2007. As expansion continues, distant galaxies redshift out of detectability. Cosmic microwave background cools below detectability. Large-scale structure disappears from view. This implies the universe becomes observationally simpler with time. This loss is irreversible. Dark energy introduces a strong time asymmetry. Early universe, increasing observable complexity. Late universe, decreasing observable information. Thus, the best time to study cosmology is near the peak of structure formation. We are already past that peak. Even though the universe persists, meaningful cosmological processes do not. Define T-cosmology, era when cosmology is observable, then T-cosmology is much less than T-total. This is a physical, not philosophical constraint. Black holes are the most entropic objects known, the final products of gravitational collapse. Entropy of a black hole scales as S proportional to m squared. Thus, larger black holes dominate entropy. Mergers increase total entropy dramatically. Estimated sequence? 10 to the 14 years, last stars fade. 10 to the 15 to 10 to the 40 years, stellar remnants decay or collide. 10 to the 40 to 10 to the 100 years, black hole evaporation dominates. Reference, Adams and Laughlin, Reviews of Modern Physics, 1997. Black hole evaporation time. T approximately 5,120 pi g squared m cubed divided by h bar c to the fourth. For a supermassive black hole, T is approximately 10 to the 100 years. This sets the practical end of entropy production. After black hole evaporation, no bound structures, no temperature gradients, no known mechanism for complexity. This state is referred to as the dark era. Relative to peak star formation, late, peak entropy production, early, total cosmic duration, extremely early. Thus, the present epoch occupies a narrow, physically special interval. Based purely on observations, thermodynamics, general relativity, and astrophysical modeling, we conclude the universe is not near its temporal end. The universe is past its peak of energy and structure. The window for complex processes is finite and already declining. The length and structure of cosmic time depend critically on a small set of measured parameters: the cosmological constant, lambda, the matter density parameter, omega m, the amplitude of primordial fluctuations, q, approximately 10 to the minus 5, the strength of gravity, g. These are not adjustable within standard cosmology. They are measured quantities. However, simulations allow us to test how changes would affect cosmic evolution. The observed value of lambda is extremely small but non-zero. Lambda approximately 1.1 times 10 to the minus 52 meters squared. Despite its small magnitude, it dominates cosmic evolution after matter dilutes sufficiently. Key result from simulations. If lambda were larger by a factor of about 10, galaxies would never form. Expansion would prevent matter collapse. If lambda were smaller or 0, structure formation would continue longer. Star formation would persist for much longer cosmic times. Reference: Weinberg, Physical Review Letters, 1987. Martel, Shapiro, and Weinberg, Astrophysical Journal, 1998. Numerical models show T obs is proportional to lambda to the minus 1/2. This means slight increases in lambda drastically shorten the era of structure. The current value allows a finite but extended stelliferous era. Interesting fact, the observed value of lambda is close to the upper limit compatible with galaxy formation. The parameter q sets the initial density contrast. Delta rho over rho approximately equals q. If q were smaller, structure forms too slowly. If q were larger, the universe collapses rapidly into black holes. Simulations indicate only a narrow range of q permits long-lived stars and galaxies. Taken together, lambda, q, and g define a narrow temporal window. The current universe lies within that window. Outside it, cosmic time is either too short or too hostile for structure. This is a quantitative constraint, not an interpretive claim. The standard LCDM model predicts heat death, but alternative scenarios exist within known physics. Big rip, vacuum decay, big crunch, ruled out by current data but historically important. Each implies a different answer to, are we near the end? If dark energy has an equation of state parameter, W is equal to P over rho less than -1, then expansion accelerates without bound. Predicted sequence: galaxies unbind, solar systems disintegrate, atoms torn apart. Current measurements: W is equal to -1 plus or minus 0.05. This strongly disfavors a big rip. Quantum field theory allows the possibility that our vacuum state is metastable. If a lower energy vacuum exists, a bubble could nucleate. It would expand at near light speed. All known physics inside would change. Timescale? Completely unconstrained. Could be vastly longer than current cosmic age. No observational evidence suggests this is imminent. Even in alternative endings, structure formation still peaks early, energy gradients still vanish, observer-supporting epochs remain finite. Thus, the conclusion that we live after the peak of cosmic structure is robust across models. Physical systems obey information constraints: finite entropy, finite information density, finite signal propagation speed. The maximum information in a region is bounded by I is less than A over 4LP squared, the Bekenstein bound. As expansion accelerates, event horizons shrink in co-moving coordinates. Information leaves causal contact permanently. Thus, the observable universe loses information content with time. This is not intuitive, but follows from general relativity. Currently, CMB temperature approximately 2.725 K. Future, T of T proportional to e to the negative HT. Eventually, CMB photons wavelength greater than galactic scales. Background becomes undetectable. Interesting fact, in about 100 billion years, the CMB will be colder than any physically measurable detector limit. Define T obs cosmo as time when cosmology is experimentally possible. This window begins after recombination, ends when horizons erase large-scale structure. We're already past the midpoint of this window. From observational cosmology, thermodynamics, relativity, astrophysical modeling, we establish that the universe is extremely young relative to its total lifetime. The era of maximal structure and energy is already past. The observer-supporting epoch is finite and declining. These conclusions are robust across reasonable cosmological models. In cosmology, observers are treated as time-dependent physical outcomes, not as fundamental entities. Their existence depends on star formation rate, metallicity evolution, availability of long-lived stable stars, persistence of free energy gradients. Thus, the number density of observers, n of t, is expected to be a function of cosmic time. In cosmology, observers are treated as time-dependent physical outcomes, not as fundamental entities. Their existence depends on star formation rate, metallicity evolution, availability of long-lived stable stars, persistence of free energy gradients. Thus, the number density of observers, n sub O of t, is expected to be a function of cosmic time. A simplified but physically motivated model expresses observer density as n sub O of t proportional to the integral from 0 to t of rho dot star of t prime times f of z of t prime times g of t minus t prime dt prime, where rho dot star of t prime is star formation rate density, f of z is metallicity-dependent probability of planet formation, g of delta t is delay function accounting for stellar evolution timescales. Such models are widely used in astrobiology and cosmology. Reference: Lineweaver, Fenner, and Gibson, Science, 2004. Numerical evaluation of these integrals consistently shows observer probability peaks after peak star formation. Typical delay, 5 to 10 billion years. This matches the Sun's formation time, the appearance of heavy elements, stabilization of galactic environments. Earth formed after approximately 80% of stars already existed. Given the decline in star formation, observer density is now near or slightly past its peak. Future observers become increasingly rare. This conclusion follows from astrophysical data alone and does not depend on biological assumptions beyond chemistry and energy flow. This result holds across spiral galaxies, elliptical galaxies, low metallicity dwarf galaxies. The dominant factor is gas depletion, not galaxy morphology. Reference: Beruzzi and Peoples, Monthly Notices of a Royal Astronomical Society, 2015. In astrophysics, metals refer to all elements heavier than helium. They are essential for rocky planets, complex chemistry, long-term heat retention. Metallicity evolves monotonically with time. Metallicity Z of T increases approximately as dz over dt proportional to rho dot star of T. Early universe, very low Z, no rocky planets possible. Late universe, high Z but insufficient gas and energy. This creates a temporal metallicity window. Measurements from quasar absorption spectra, galaxy surveys, stellar population synthesis show rapid metallicity rise between redshift Z equals 6 and Z equals 1. Planet formation requires cold molecular gas, dust grains, disk stability. As gas reservoirs deplete, disk formation becomes rare. Planet formation rate declines faster than star formation. This implies even if stars continue forming, planet formation efficiency drops sharply. Combining metallicity growth, gas depletion, and stellar lifetimes, we find habitable conditions rise sharply, plateau briefly, then decline irreversibly. This asymmetry is entirely physical. Red dwarf stars, M-type stars, constitute some 75% of all stars. They burn hydrogen extremely slowly. Lifetimes up to 10 to the 13 years. They are often cited as extending the cosmic habitable era. However, astrophysical constraints include intense stellar flaring, tidal locking of planets, narrow habitable zones. These effects reduce stable surface conditions and atmospheric liquention. Even red dwarfs must form from molecular gas. They will stop forming once gas is exhausted. Gas exhaustion timescale, 10 to the 13 years. After this, no new stars of any type form. After stars die, white dwarfs cool toward equilibrium. Temperature asymptotically approaches background radiation. Cooling time, 10 to the 15 years. At this point, no significant energy gradients remain. Even under optimistic assumptions, future complex systems are limited. Energy throughput declines monotonically. Entropy dominates dynamics. This is independent of biological specifics. Reference: Atoms, Journal of Cosmology and Astroparticle Physics, 2008. While total entropy always increases, the rate of entropy production is time-dependent and physically meaningful. Define S dot of T equals ds dt. This quantity tracks energy dissipation, structure formation, and irreversible processes. In cosmology, entropy production is dominated by stellar fusion, supernovae, and accretion onto black holes. Detailed calculations show entropy production peaked at redshift z approximately 2, corresponds to peak star formation and quasar activity, roughly 10 billion years ago. This result emerges independently from star formation history, black hole accretion luminosity functions. The universe today produces far less entropy per unit time than in the past. Entropy contribution comparison. Source: Relative entropy contribution. Cosmic background radiation: negligible. Stars: small. Supermassive black holes: dominant. Even now, 99.9% of entropy resides in black holes. Stellar processes are secondary. This dominance increases monotonically with time. Although total entropy increases, S dot of T declines. Energy dissipation slows. Physical processes become sparse. This is a quantitative statement, not qualitative intuition. Periods with high entropy production lead to rich structure. Low entropy production lead to simple dynamics. The present epoch lies before maximum entropy production, before entropy saturation. This defines a finite temporal interval of complexity. Analytic solutions are insufficient for nonlinear structure formation, feedback processes, gas cooling, and star formation. Thus, cosmologists rely on n-body simulations and hydrodynamic simulations. Major simulation projects: the Millennium Simulation, Illustris, and Eagle. TNG 50. Common findings: star formation peaks early. Massive galaxies assemble quickly. Late-time universe becomes dynamically quiet. Reference: Springle et al., Nature, 2005. Vogelsberger et al., Nature, 2014. Simulations show maximum number of star-forming regions occurs early. Merger rate declines rapidly. Gas inflow shuts down as expansion accelerates. Quantitatively, merger rate of T is proportional to 1 plus z to the m, where m approximates 2 to 3. Thus, structural novelty decreases with time. When simulations weight time by star formation, planet formation proxies, energy throughput, they consistently show the highest probability density for observers occurs before the present. Long future contributes little despite its duration. These results are independent of biological assumptions, stable across simulation codes, and insensitive to moderate parameter variations. This strengthens confidence in the timing conclusion. Accelerated expansion creates event horizons. Consequences: regions exit causal contact permanently. Information encoded in matter and radiation becomes inaccessible. This is governed by R event equals A of t times the integral from t to infinity of A of t prime dt prime. As time increases, observable co-moving volume decreases. Total accessible information declines. This is counterintuitive, but mathematically unavoidable in lambda-dominated universes. Predicted sequence: galaxies redshift beyond detection. CMB signal disappears. Primordial nucleosynthesis evidence erased. Future observers cannot reconstruct cosmic history, cannot measure expansion. Reference: Krauss and Scherer, General Relativity and Gravitation, 2007. Currently, CMB measurable, galaxy distribution observable, expansion parameters accessible. This condition is temporary and already degrading. Combining entropy production decline, information loss, structural simplification, we see early universe increasing observability, late universe decreasing observability. This asymmetry emerges directly from general relativity and thermodynamics. A common mistake in reasoning about cosmic time is treating all moments as equally relevant. In physics, time must be weighted by physical processes. Define a weighting function W of t based on energy dissipation, star formation, structure formation, entropy production. A physically meaningful probability density is then P of t proportional to W of t, not P of t equals constant. This distinction fundamentally alters conclusions about typical cosmic times. Using the cosmic star formation rate density rho dot star of t, define P star of t equals rho dot star of t times the integral of 0 to infinity of rho dot star of t prime dt prime. Empirical result, P star of t peaks at t approximately 3 to 4 gigayears, falls rapidly after t approximately 10 gigayears. Thus, the present epoch lies on the declining tail of this distribution. An alternative weighting uses entropy production. Ps of t equals s dot of t over the integral of 0 to infinity of s dot of t dt. Using estimates from stellar fusion and accretion onto black holes, result, entropy production peaks at redshift z approximately 2. Long future contributes negligibly despite its duration. Reference, Egan and Lineweaver, Astrophysical Journal, 2010. Although the future lasts vastly longer, W of t approaches 0 as free energy vanishes. Contributions to integrals converge. Mathematically, the integral of t0 to infinity of W of t dt less than infinity. This is why a finite era dominates physical relevance. Duration alone is not decisive. Whether weighting by star formation, metallicity growth, entropy production, black hole accretion, the result is consistent. The physically significant epoch is early and finite. The conclusion that we live after multiple cosmic peaks must be tested against different expansion histories, different cosmic beginnings, different late-time behavior. This ensures robustness. In cyclic models, universe undergoes repeated expansions and contractions, no absolute beginning in time. However, entropy increases with each cycle. Later cycles are longer but less structured. Mathematically, Sn+1 is greater than Sn. Thus, structure degrades across cycles. Observer supporting conditions remain temporally limited. In eternal inflation, space inflates indefinitely. Pocket universes form continuously. However, within any given pocket universe, standard thermal and structural evolution applies. Thus, star formation still peaks early. Entropy production still declines. If lambda equals 0, expansion decelerates, structure formation continues longer. However, gas is still finite, nuclear fuel still exhausts, entropy still increases. Even in this case, peak complexity occurs early. Late-time universe becomes dynamically quiet. Reference, Peebles, Principles of Physical Cosmology, 1993. Across lambda CDM, cyclic models, inflationary cosmologies, the following remains invariant. Finite structure supporting epoch, early peak in energy dissipation, declining complexity with time. Grand unified theories predict proton decay with lifetime tau p approximately 10 to the 34 to 10 to the 36 years. If true, all baryonic matter eventually decays. Stars, planets, and atoms dissolve. Current experiments set lower bounds but no detection. Reference Super Kamiokande Collaboration 2020. After proton decay, matter converts to leptons and radiation. Electron-positron annihilation dominates. Energy scales extremely low. No bound structures possible. Some dark matter candidates are metastable and decay on timescales much greater than 10 to the 26 seconds. Decay leads to further homogenization, increased entropy, and reduced structure. Eventually, all matter and radiation dilute. Vacuum energy dominates dynamics entirely. At this stage, rho matter is much less than rho lambda. Expansion becomes A of t is proportional to e to the ht. No known physical process can reverse this trend. From fundamental physics, microphysical processes terminate early. Macroscopic structures vanish next. Expansion persists indefinitely. Thus, physical activity is front-loaded in time. The present lies deep within the active era, but past several maxima. A common intuition is that if the universe lasts extremely long, observers should mostly exist very late. This intuition is physically incorrect because it ignores energy constraints, entropy growth, and finite structure formation. In cosmology, time is not sampled uniformly. Observer emergence can be treated as a rate-limited process analogous to radioactive decay or star formation. Define gamma observer of time is equal to observer production rate. This rate depends on star formation, planet formation, energy gradients, and stability of structures. As shown earlier, gamma observer of t goes to 0 as t goes to infinity. Even though future time is vast, observer production rate becomes negligible. Integrals over time converge. Formally, n observer is equal to the integral from 0 to infinity of gamma observer of time dt is less than infinity. This is a strong mathematical result. It implies that the total number of observers is dominated by a finite early interval. Using realistic astrophysical inputs, the median observer time occurs before the present. The present epoch lies on the late side of the observer distribution, but not extremely late. This result appears in star formation-weighted models, metallicity-weighted models, and entropy-weighted models. Late here means after multiple cosmic peaks, not near the end of cosmic duration, not near the end of physical processes. This distinction is often misunderstood. The timing of the present epoch has been constrained by independent branches of physics: observational cosmology, stellar evolution theory, thermodynamics, general relativity, particle physics, large-scale numerical simulations. These methods do not rely on each other, yet they converge. Expansion accelerates, observable structure declines, event horizons form. Astrophysics: star formation peaked billions of years ago. Metallicity growth saturates. Gas reservoirs deplete. Thermodynamics: entropy increases. Entropy production rate declines. Free energy vanishes asymptotically. Relativity: event horizons limit future observability. Information is irreversibly lost. Reference Krauss and Scherer, 2007. Particle physics: baryonic matter may decay. Stable structures are temporary. Changing cosmological parameters within error bars, star formation efficiency, galaxy feedback models does not change the qualitative outcome. The universe's most active and structured phase is finite and already past its peak. Are we near the end of cosmic time? From physics alone, the total lifetime of the universe is extraordinarily long, possibly infinite under LCDM. Therefore, no, we are not near the end of cosmic time. Are we near the end of the active universe? Using measurable physical criteria, star formation, energy dissipation, structure formation, observability, the answer is different. The universe has past peak star formation, past peak entropy production, past peak observability. Therefore, we live after the most active phase of the universe, but long before its final state. The present cosmic time can be described as early relative to total duration, late relative to energy production, late relative to structure formation, transitional relative to long-term thermodynamic equilibrium. This characterization requires no philosophical interpretation. None of this follows from human intuition, everyday timescales, simple extrapolations. It emerges only when observations, equations, simulations, thermodynamic constraints are combined. Several uncertainties remain: exact nature of dark energy, the stability of the vacuum, proton decay, ultimate quantum gravitational effects. These affect details, not the overall timing structure. From all currently available evidence, the universe is far from its final thermodynamic state. The era capable of producing complex energetic structures is limited. The present lies beyond several cosmic maxima, but within that finite window. This is not a speculative claim. It is the combined outcome of modern cosmology, astrophysics, and thermodynamics.